Thank you very much. So, as Thomas was saying, Alvaro here is a PhD student of Lars Roque-Verhelden and myself. And when he came to us, he was already interested in multi-agent systems. It was something he had worked with at undergrad at the university, and he came to us and he said, okay, I want to maybe, hopefully work on this on my PhD. And we looked at it, we were not familiar with multi-agent systems before. We looked at it, and because we were already familiar with Erlang, and we thought, okay, there is a match here. So what is a multi-agent system? Anybody? Erlang systems, okay? So the way people define this is that a multi-agent system is a system composed of agents, of intelligent agents, which have also an environment. The system includes the agents and the environment that surrounds them and that they interact with. Some examples of multi-agent systems are, for instance, online trading, disaster rescue, and so on. And there is a big, large community working on research on multi-agent systems. So this is not a multi-agent system, but we could program this as a multi-agent system. I have this picture because I think it's fun. It's just from the RoboCup initiative. I don't know if you know about this initiative. This was a grand challenge, something like 30 years ago, and they said then, in 50 years' time, we should be able to create a football team of robots which can win, which can beat a human world champion football team. That was 30 years ago. I think they are a bit far from that. But anyway, this was the idea, and I want to use this to illustrate some ideas on the multi-agent systems. So, simply put, an intelligent agent is an entity which has some sensors, receives information from the environment, and then does some thinking, and then it actuates over the environment. So in the example of the RoboCup, we can say that there is this football player, this agent, that is close to the goal, and it receives information about its distance to the goal. It has information about the opponent position, and then it thinks, and then it decides, for example, to kick the ball and try to score. It has a goal, which is to score, and then depending on the information it gets and its own intelligence, it's going to do something to achieve this goal. Some characteristics, some very important characteristics. What does it make an intelligent agent? Is that they should be autonomous. And by this, we mean that, we, as people or as programmers, delegate our goals to these agents. So we give them some goals, but they should be able to determine their course of action, what they should do to reach those goals in an independent manner. They should also be proactive. So in order to reach those goals, they should do something about it. They should try to achieve those goals. So we are ruling out passive agents that are just there sitting, waiting for something to happen. They should try and reach their goals. They are also reactive. They should also be reactive. So of course, as we have shown in the previous example, they react to the changes in their environment. And they should also possess some social abilities. So they should be able to cooperate and coordinate among themselves in order to reach their goals. They may have a common goal, but each one has their own goals, okay? And I think all these characteristics tied somehow nicely with many things I have heard in these talks at the Airline User Conference. I have heard about autonomy, I have heard about social abilities, cooperation, and so on, dependencies. So I think it's, even if this comes from the multi-agent system community, I think this, in some sense, applied to us, maybe, and to the systems we want to build. So let me put another example, a very simple example. Let's say that what is a day in an agent's life? So, okay, the agent leaves home, is going to walk to the office, do some work, and then come back home. Okay? Okay. So, somewhere in the 80s, there was this philosopher. Sorry, I'm not sure if he's still alive. Sorry about that. I don't know. But anyway, there is this philosopher called Michael Bradman, who was researching on human practical reasoning. And he came up with this idea on how practical human reasoning is built up. And he, or from his ideas, came this what is called the belief, desire, intention model. This is something which is very well known in the multi-agent systems community, in the people that are building intelligent agents. It's called the BDI software model, or the BDI architecture. And the idea here is that agents have a mental state, and they have a separation of concerns. So on one hand, they have their beliefs, which is how the information they have about the world. And I should stress that this information may not be accurate. So this is information they perceive. So for instance, I can look at this guy here as an agent, and I can think, oh, because he's looking at me, he's probably interested in what I am saying. But maybe he's thinking about something else, completely different. Okay? So this is my perception. These are the beliefs. Then agents have desires, which is, what do they want to do? What is their goal, okay? And they have intentions, which is, how are they going to do it, okay? So there is a separation between what I want to do and how I'm going to reach that goal that I want to achieve. And this, I think, again, I want to stress that what the work we are presenting here, we think it is interesting for people building multi-agent systems, but we think that maybe you can get some ideas from here when you build your own software. For instance, if you are building protocols, communication protocols, and so on, maybe you can get ideas from this. So, okay, if I go back to the example I showed before of the agent that goes to work and does some work and then comes back home, I could say, okay, this agent has a belief, an initial belief that it's at home. A desire, I want to go to work. And then what the intentions are the steps to fulfill this desire. To go to work, I need to leave home and walk to the office. Okay, this I have already said, that the central idea in this is that computer programs may have, or behave as if they have a mental state. And they have these components of beliefs, desires, and intentions. So let's go back to these goals. So the agent has the goal to go to work. So the steps it's going to follow is, okay, I have to leave home, and I have to get to work. And these steps, what we call a plan, brings up new goals, which is, okay, now I want to walk to work. I need to fulfill that goal in order to follow the steps that allow me to reach the previous goal, the initial goal. So goals, desires are divided into sub-goals, okay? And there is this way of working. Okay, what if it rains? I want to walk to work, but then it rains. What do? I can take an umbrella, or I can go to work by car. What it means is that, as I said at the beginning, the agents have to react to changes in the environment. So they are in the process of doing something, but then some event, something new comes up, and then they have to adapt to that, okay? So the same goal may have different intentions, different means to be reached, depending on the situation. So, of course, this can become more complicated, and okay, to drive to the office, the agent needs to have a key, the car has to be close by, and a lot of things. So, okay, this is just an example. So this is what is called this procedural reasoning cycle. So this is how the agents reason. So this is just showing what I have explained in the example. We have these three components: beliefs, desires, and intentions. And there is also a set of plans, which is what the programmer has programmed, that, okay, all the things the agent can do. So I'm just showing how this reasoning cycle works. The agent has the desire to get to work. The beliefs at the time are he's at home, it rains, and so from the plans he's going to choose drive to work. Again, this separation of deciding what to do and then doing it. Okay, how do I program that? What language can I use? Any ideas? Java? Anybody else? JavaScript, great. More? No? Come on. Come on. Erlang. I thought I was in the Erlang user conference. Yes. Maybe I was mistaken. Oh. So yes, of course, I can program this in Erlang. Great. Yes, this is the way to go. Because, you know, multi-agent systems, we have concurrency, distribution, we want to have fault tolerance. Of course, Erlang is the perfect match. However, we look into what people at the multi-agent systems communities are doing, and they actually have their own programming languages for this. And one such example is JSON. So they have built their own programming languages that are talking about beliefs, desires, intentions, and so on. So they have this level of abstraction, which is very good. And they have done a lot of work on getting this reasoning cycle right, which is very good. Why do we have to re-implement that? And not only that, we also think, oh, if we want to talk to these people, we actually need to talk their language. If we go there and say Erlang, they say, what? So, okay, let's look at this JSON. Let's look at this JSON and see. So, yes, JSON implements this BDI architecture and this reasoning cycle, and yes, it's using Java below. Fine. Okay. So let's look at an example of JSON code. So this is the code of the agent that goes to work. Luckily, or I know by chance, it happens that this JSON is also inspired by Prolog. Ooh, wow! So it has some similarities with Erlang. Nice. So beliefs. These are predicates with ground terms. Okay, so we have the predicate at home. Desires. They are marked by this bang. This is a desire. And then plans have three parts, which have first a trigger, then after the colon, it's a kind of guard. So if the agent is at home, then it can fulfill this plan. And then the body of the plan, which is in this case, new goals, to leave home and to drive to work. In the case of the goal to leave home, what we see here, this minus at home means that the belief at home is going to be removed from what is called the belief base, where the beliefs are stored. And a new belief is going to be added to this belief base. So that's how it works, okay? Questions? Okay. So far, I have been talking about one single agent, but of course, what we want is to build multi-agent systems made of many agents. So this is just one classical example of, because I want to be politically correct, it's me, a female sitting at home and wants to drink some beer, of course, why not? So there is this, this agent which I delegate my wish to get some beer from the fridge, and there is this robot that brings me the beer, and when the beer is finished in the fridge, it would contact the supermarket and ask for more beer to be delivered. Okay. How do we do that? Well, of course, we need communication. So how do we communicate in JSON? Well, it has similarities with Erlang, at least syntactically. So I have two agents here, Tom and Bob. Actually, now it's Alice. I don't know what happened. Anyways, so we have some actions, and this is a send action that what it does is having the name of the agent I want to send a message to, having in this case, a directive, I think it's called tell, doesn't matter, and then the message, which is hello. And what this does is the agent Tom, when this code gets executed, is going to put a belief hello in the belief base of Alice. So that's how communication is done. Okay? So JSON has some very, very good characteristics. Okay? As I said before, there is a lot of effort in getting this reasoning cycle right and so on and so forth. But it has some deficiencies as well. On one hand, we all know, I think, here that concurrency, it's a difficult problem to get it right. No? No? Somebody there say no? Okay, great. It actually, the language itself has no distribution mechanism. So they rely in other libraries, in other in other libraries or other tools to distribute multi-agent systems. And same thing can be said about fault tolerance. And actually, you end up, the people who are using JSON for implementing multi-agent systems, they end up writing a lot of Java code, pure Java code, okay? So we say, okay, this is very good. This is very good, because then we can come in and say, okay, let's do something about this. And we have a very good tool, which is Erlang, which is good at concurrency, but especially in this case, what is very key is that it's very good at distribution and is good in fault-tolerant mechanisms, okay? So let's borrow ideas from Erlang and put them into JSON. Put them into JSON, okay? Yeah. And this is what we call, or Alvaro here calls eJason, very original, eJason, Erlang JSON, yes. And there is there you have the GitHub repository where you can download it and use it. Okay, so what does eJason do? It corrects some of the concurrency problems. I'm going to tell a little bit about this. I'm not going to tell a lot, so if somebody is interested about the concurrency problems of JSON, we can take it offline or after if we have time, whatever. But the message here is that we are looking at the JSON people and saying, you see, it's not so easy to get it right when it comes to concurrency. So we have looked into your language and we found there are some problems. Many of them they already know, of course. We have, as I said, extended the JSON language with distribution and fault-tolerant mechanisms inspired by Erlang, which makes, I think is good because it makes that people that don't want to know anything about Erlang but want to use JSON, they can use distribution and fault-tolerant mechanisms in their favorite language, and they don't have to care about Erlang. And there is this work on implement, and you can find it in the repository, the JSON interpreter implemented in Erlang. Okay. So Alvaro here discovered many problems of many concurrency problems in JSON. I'm just going to talk about one, just to give you a feeling, one idea or one problem, so to say. And this is when agents have desires that cannot be completely fulfilled. So, okay. So let's say that this agent wants to go home and tidy the kitchen. Okay. In JSON, this may have two outcomes. So in JSON, the agent either goes home and cleans the kitchen, or just goes home. Because when it tries to clean the kitchen, and it cannot because it's not at home, then this plan is dropped. So this is what we would call a race condition in some sense, no? In the sense that there are two possible outcomes. It's not deterministic. So in the implementation that Alvaro has done, he just, this is not happening. So there is only this plan of tidying the kitchen is not dropped when it's not abandoned when it cannot be fulfilled. But the only outcome is that the agent goes home and tidies the kitchen. This is just one example. And as I said, the idea is that, yes, concurrency, it's hard. And we should be happy that we have Erlang. So with regards to distribution, an agent is implemented as an Erlang process. In multi-agent systems, or at least in the languages like JSON, agents are distributed into containers, but we can map a container to an Erlang node. And something that is also done in the implementation is that agent names are unique, globally unique, okay? And this is what Alvaro has implemented and called a distribution manager. So the names of the agents are unique, and he maybe tell you a bit more that when it comes to fault tolerance. Okay, so this is just an example of the distribution schema where we have two hosts and one container running in each of the hosts, and is the example of me sitting at home and wanting to drink some beer, and okay, so some of the agents are running in one container and some others in other container. This is for Erlang people. This is so what? So I won't say more about this. It's just the nice thing that this is in the level of eJason. Okay, so now let's move into fault tolerance, and I'm going to pass over to Alvaro.
Okay, so hello. So just summing up a bit, what we did is, this JSON language was out there. The people from the multi-agent community were saying, okay, I can program software based on the VDI model. My agents are communicating. I have a lot of entities, but they couldn't distribute their software. And we said, okay, why? What's the problem? No, Java, concurrency is not very good at that. And we said, okay, we have Erlang for that. And as Clara said, we introduced, there was not the agent containers and all that. We introduced them from the distribution paradigm of Erlang. And apart from providing such distribution schema, we said, okay, now you can distribute your agents, but you have paid almost to no attention to fault tolerance. You have agents. If they crash, nobody's caring. You cannot recover your system from problems in your agents. And Erlang is very good at that. So we said, okay, let's bring the best of Erlang into this language. And we introduced both fault detection and fault recovery techniques inspired, but not equal to those of Erlang. We introduced a monitoring mechanism. As you know, it allows us to know if some other agent, in Erlang is a process, in eJason is an agent. You can know if another agent is dead, or you can know if it's disconnected. Okay, so you are notified about this change of execution state, and you react to it. We implemented a monitoring system. An agent can monitor the execution state of another agent. But apart from being aware of deaths and disconnections, we increased the observational power of monitors, which may be interesting also to Erlang. For instance, because now the monitoring agent is able to know if another agent appears. What does it mean? You have an agent saying, okay, I want to monitor a book selling agent. If it's not available at the time you're establishing the monitor, once it appears, when that agent, that process is spawned, you are notified. Now in Erlang, you cannot be notified about some other process you have to communicate to, you are not notified of its existence. Okay, you can use then a name of an agent as a contract of its functionality. Okay, you say, okay, I want to monitor the bookseller. Once it's available, notify me. I want to communicate to that agent. Apart from that, we also allow monitors to know if the presence of another agent is similar to the one before. Okay, you say, I want to monitor the bookseller, and the eJason runtime system notifies me this is not available and will notify me again when this is available. Apart from that, the monitoring agents can know if some other agent has been revived, for instance, by a supervisor. Okay, we are communicating to some other agent, and if it crashes and comes up again, so the monitor notifies us. We can know that maybe our session or communication information has been lost. Okay, so as I said, we introduce monitoring with enhanced observational power. What is also important from monitors in eJason is that the notifications in Erlang that are messages here are beliefs. Okay, we've tried to map Erlang concepts into JSON. As Clara said, we wanted the community, the multi-agent system community, to feel comfortable with this language. We didn't want them to learn Erlang. We want to use their ingredients with the potential power of Erlang. And now here, monitoring notifications are just new beliefs. It maps perfectly. They have nothing new to learn. Apart from that, the monitors that we implemented now are persistent. What we mean by that is that now in Erlang, you establish a monitor, the monitor agent, the monitor process dies, you get a notification, and the monitoring relation is done. You will never know if it's up again or if it respawns and dies again. Our monitors persist. You can know what's happening. If you're interested in the execution state of another agent, you establish a monitoring relation, and you know what's happening with that agent. You know if it dies, if it's up again. You have more information. Normally, you monitor another agent because you want to interact in some way, so the more knowledge you have about its execution state, the better, or that's our intuition. So this is all about monitoring relations in eJason, which is a fault detection. You see that you are able to detect faults, but you have to implement how to recover from them. And on the fault recovery dimension, we implemented a supervision mechanism which is inspired by Erlang, but it's not exactly the same. You see here we have monitors, agents monitoring other agents. We have a supervising. We have a supervision tree, but this tree is dynamic. Okay, that means that an agent can say, okay, I want to supervise this set of agents with this strategy, but it's established at runtime. You don't need to say, okay, this is a supervisor agent that spawns these other agents which have this behavior. Everything is dynamic. You can establish and disable supervision relations online. Also, it's important to notice that supervisors and children, supervisors and the supervised agents are not children. They are not coupled. A supervisor an agent can supervise a set of agents, but if the supervisor dies, the agents are not dying. You are not introducing any kind of strong dependencies between the agents in a supervision relation. And the most important contribution of the supervision in eJason is that not only the supervisor will restart the agents when one of them dies. You not say, okay, I want to supervise this one, and if one of them dies, bring it up again. We also introduce a mechanism that allows the detection of misbehaviors in the supervised agent. We do this by introducing a pinging policy. Okay, we have, for instance, an agent Tom supervising an agent Alice, and it's constantly pinging Alice, and Alice is responding back. Everything is done by the runtime system. Okay, a programmer just has to say, okay, Tom supervises Alice, and forget about this. Okay, you just win the behavior that I'm going to describe now. The runtime system will be polling Alice, pinging, to know if it's alive, if it's responsive. When Alice is not responding, it's alive but not responding, it sends an unblock signal. By the nature of JSON, it's possible that during the computation of guards, the agent can enter in infinite loops or computation that are so long that won't terminate, or it cannot be tell if it will terminate in real time. And this supervision mechanism will allow telling if an agent is alive but unresponsive. Okay, you not only recover edges that die, but you can tell if they are actually providing any behavior. If they're not, the supervisor automatically unblocks them. Okay, it will say, by the nature of JSON, it's only possible to fall into an infinite loop during reasoning when you are assessing the truth of some value. So you say, okay, unblock it, assume it's false, and the agent will continue, will be responsive again. If such unblock happens a lot of times, also eJason will restart the agent. Okay, what it does is allows to identify an unresponsive agent, and if it's misbehaving, just restart it by itself. The program doesn't need to care, okay, make some test if the agent is sensible. No, if something's going wrong, it will automatically restart the agent. And I'm just finishing, okay? The idea just that I want to transmit here is we said, okay, Erlang is a good language in order to program highly concurrent distributed system like the multi-agent systems are, but the community is not using it. I mean, the focus of the community is handling the high-level abstraction for agents like the VDI model, how to program a reasoning cycle, but they didn't care about how to distribute. Actually, they lived quite happily without having distribution and a sensible concurrency framework. And we said, okay, why not use Erlang underneath? And you're going to gain all this potential, all this efficiency in the distribution and fault tolerance even. And we wanted to do that without they even noticing and with a very short learning curve. And that's why we put Erlang underneath JSON in order to build an interpreter that implements all the behavior of JSON and introduce all the excellent distribution and fault tolerance capabilities of Erlang. And we call that eJason, which is what we try to sum up today to you. And if you find that interesting or have any doubts or you want to show it running actually, we can do that afterwards and we'll be happy to. So this is it. Thank you.
Any questions from the audience?
Hi. What's the execution model of the rules to go to the next stage? Is something like data log or prologue, or how do you interpret the what to do next and how do you execute?
There is a reasoning cycle. I mean, there are like 12 steps, and they are implemented in Erlang. It's quite the formal semantics of JSON is available, and we implemented them. I mean, it says if their beliefs are this, the next step is to be that, and we implemented all those transitions. We implemented them in Erlang.
I've got another question on a slightly different level here. So you said in the beginning there was a football play, and this is the vision. What is the kind of the hardest problem people using JSON are trying to address at the moment? Mm-hmm. And how does your Erlang solution solve that problem for them, and you can make much more progress in the artificial intelligence world?
Wow.
I mean, one thing I would say is that one problem they face is that they don't scale up very well. So they can only run okay, it's not the case maybe in the RoboCup. If you only have one agent per robot, but in general they have problems with scaling up. They cannot run the large number of agents that you can in Erlang. So they have protocols where they want to try and use with a large number of agents. So that's one of the problems. I don't know if it's the main, probably it's not, but it's one of the problems. Yeah?
Well, actually, I think the main problem they have is distribution. There are a lot of implementation of third-party software that is meant only for distribution. There is some software called Jade that different languages. I say, okay, I delegate all my communication, all my distributed communication to Jade. You have to program integrated to this third-party software. I provide you a language where agents can interact, but I don't provide you the means for them to interact distributed. I mean, they have problems to run separately in a distributed manner their software. They said, okay, this should be possible, but they didn't make the effort. I think they desisted on it because it was not an easy task.
Yeah, so I see that you can add these kind of capabilities to the language. My really question is, how does the robot look like if you can do all these kind of things? What kind of things can you do in reasoning which you can't do today because you can distribute, because you have a better concurrency model? What kind of things can you then envision we have in the future?
Well, you can do things that you couldn't do in a mainframe system. I mean, if you have only one container, one computational system, what can you do there? I mean, you cannot you cannot build an e-commerce system. You cannot build anything apart from what has to be run in your own laptop or your own device. I mean, anything that is distributed, you cannot do in multi-agent system.
Or you have a lot of problems.
Yeah. Well.
Any more questions from the audience?
Hi.
Hi.
Can you distinguish between false and undesirable reasoning?
No. I mean, it is assumed that is a fault. Anything that is not expected with regard. I mean, we focused on the things that obviously were faults. What is obviously a fault is having an unresponsive agent. I mean, if an agent is not responsive, what's the use of that agent? It's an infinite loop. I mean, this is for sure a fault. If an agent is crashing, it's a fault. I mean, if the programmer establishes a supervision relation saying, I want this agent alive, and this dies for some reason, it's a fault. I mean, but if you have an agent that is saying, computing something and saying it's 5, you don't have the means to say, okay, if it's just 5, this agent is not acting as it should. I don't know if it's that answer. I mean, we focus on what was obviously a fault or what we understood to be obviously fault. Business-like faults, we didn't focus in them. I mean,
Just, I would like to add, it's not regarding to that, but what your previous question is that we contacted one of the creators of JSON, and we showed him this, and he was very, very positive. He particularly liked this idea of that you could check diverging agents that are alive that you cannot communicate with, and so on. So he really liked it. So one of the goals that I said at the beginning, okay, we want to be able to talk to these people in the multi-agent community, at least to some extent we reach it, and they say, oh, this is very good, and yeah, so I just wanted to say it.
okay.
Time for one last question, if there is any. If not, then let's thank the speakers again. Thank you very much.
Thank you.